Up next, we have Csaba from the core gas team. He will be talking about scaling and P2P on Ethereum.
Thank you. Thank you. So yeah, I'm Csaba, working on the gas team, but I'm also kind of working on the P2P implementation all over from EL to CL to Lean. So yeah, scaling. We are scaling. The L1 is scaling, the L2 is scaling. And we plan to continue this, right? And to do that, we have this thing, the peer-to-peer network, that we also have to scale, unfortunately, or fortunately. So for those who are just building on Ethereum, Ethereum is one of those almost unique blockchains that are actually decentralized. So we do tend to run on a peer-to-peer network of 10,000 nodes. And each one of these nodes has an EL client and a CL client, which are kind of on the same node. Between them, they are communicating on this so-called engine API. But yeah, there's a network in between. And when we are scaling, we have to think of this network and how we scale it. And I will be speaking of this. So when you are thinking of this peer-to-peer network, it's not just the peer-to-peer network, it's a bunch of peer-to-peer functions. And actually, we have two peer-to-peer networks, one for the EL clients and one for the CL clients. And each one of them have their own nice little functions, discover nodes, manage the peer sets, synchronize the data when you are starting it up. And then for the EL, it has to handle the mempool, basically the life of the transactions before they are getting on chain. And then the CL has to handle the block diffusion, attestation, and the dispersal of blobs, functions which are needed to actually make the consensus happen. So kind of after the block has been produced, life of the transactions. There are also a number of protocols. So Discovery, V4, V5, Dev P2P on the EL side, Lib P2P on the CL side. I'm not going into the details of this one. Just appreciate the complexity of the picture. And when we are scaling, we actually have to scale all of these. Now, I won't be speaking of all of these. I will be just speaking of a few, starting with the CL, and then going a little bit into the EL. So let's see blob scaling. So, yeah, actually, almost 2 years ago, I was publishing a write-up on Fudas, which I was updating kind of a year ago, which was a plan to get to 256 blobs. And we are kind of following some parts of this plan. Obviously, plans are changing, so other parts are not followed or changing. But some parts of this are already going. So we have in this plan, we have repairing the network, which we have now. We have cell-level messaging. We have block-level encoding. And then in the second version that I published, there was also the get blobs, an enhanced version of that, and a random linear coding-based sampling. So here you see with green the things that we are basically having now, and with blue the things that we are kind of working on. And then there's other white ones which are either happen or not. We will see based on how plans are changing. So a little bit about cell-level messaging. Cell-level messaging is simply the fact that we are sending small messages, which has actually a bunch of advantages. It's an improvement on the PIRDAS concept that we have now, where we are sending whole columns. So a bunch of blobs bundled together, then cut into pieces, and then these columns are being sent. With cell-level messages, we can do more. Actually, we can do less in the sense that we have to use less bandwidth to achieve the same function. And we can speed up also the diffusion. Then there are other functions which we don't do that. But what we do, actually planning to do now, is to add row topics. So adding row topics means that the reconstruction, which is happening in the network, doesn't need supernodes. So what we have currently in the current system with PIRDAS is that whenever you need to reconstruct the blobs from the original coding, then you have to be a supernode, which is kind of getting all the data, and then only those can reconstruct. With this little trick, we can go into something which is a partial reconstruction, which is taking out of the picture supernodes, which is always nice in a P2P system, even if we don't need it in the sense that we do have supernodes. And then server messaging also allows other tricks, which we are not doing yet, and we are discussing whether to do things similar to this. So the original plan was to do this second layer of Reed-Solomon coding. And another plan that I was outlining there is to do another type of coding, which is a random linear coding over the blob content in a block, which has advantages. It means sampling can use less samples. It means reconstruction can go easier from the cells. Okay, that's about blob diffusion, but we also have the blocks. So let's see block diffusion. Now for block diffusion, we are doing a bunch of things, actually. This is a presentation that I was doing in the LIP P2P summit in Cannes. Just a slide of it. If you want to see the details, you can go to the QR code. We have this kind of, I'm calling it low latency P2P toolbox. So we have a number of tools that we can use to make the diffusion faster, so that then we can shrink the slot time, increase the bandwidth, increase the block size, and so on and so forth. Some of them we already did. Those are the green ones again. So we have batch publishing, which is helping us send out things fast. We have quick transport now, and then some of others we are working on. So the segmentation and the encoded sending of the data, Azure-coded sending is something that we are working on now. Overlay optimizations is something we are working on down, and there are others which we are not working on currently. Okay, that's for the CL. Now let's speak about the execution layer. So we could speak about discovery peer management sync. You can find my other presentations on that. I didn't put a QR code, but the mempool is kind of, I think, the next horizon in many aspects, because in the mempool we have lots of work to do. So today, if you look at the mempool, you see basically this. The figure is showing you take a transaction, and based on how many nodes of the 10,000 has it in the mempool, you put the transaction either on the right side or on the left side. And you basically see that everyone is on the right side, which means everyone has all the transactions. Today, the mempool is basically fully synchronized among the nodes if you look at it at the time scale of a slot. So if you would look at just when the transaction was sent, then obviously one node has it, but then it quickly propagates and then everyone has it. And that's very nice. We have it for the normal transactions, we have it for the blobs. The only problem is that tomorrow this cannot be true, because this would mean that everyone is handling the whole capacity of the network, and that's not what we want. That's not scaling. So we have to change this. We need nodes to have partial views for the blobs and partial views for the transactions. So scaling the mempool, it kind of means two things. On the left side, I have the typical, what people think of. We need to use less bandwidth. And on the right side, I have another more hidden thing that is typically coming up in scaling. When you are designing a system to scale, you should think of how it's working when for some reason, you don't have the capacity. And you can design it in a way that it's basically has a harsh drop in throughput when you are, for some reason, this happens. There is an internet issue. Or you can design it that it still keeps nice throughput. You can think of this at the system level, where the whole system should have a throughput, or you can think of it at your nodes level. Your node has an issue. You happen to run it at home. We like those. You happen to watch a movie, which happens to be in 4K, and then your node starts to suffer. But you don't want it to drop to zero. You want it to still work somehow. So anyway, on the left side, so reducing bandwidth. We did it already on the CL side. Pildas was very nicely doing it, making it much less. And we have to do it also on the EL side now. So what we do on the EL side, we have a few proposals there. Maybe the most important is sparse blob pool, EIP 8070. This is reducing the bandwidth in a similar fashion as we are reducing it to the CL somehow. We are having only part of the nodes having the blobs, and others are sampling it only. And then we have different sharded designs, mostly on research posts. We can think of the sharded blob pool, which has different versions, horizontal, vertical. And then you can also think of a sharded mempool, that it's not just the blob transactions, the big ones, but you are sharding the mempool in the sense that not every transaction is going to everyone, and you are organizing that in a nice fashion. And then there's the question of, can we really scale? Well, the problem with scaling, again, is that it's nice how we operate with trying to find a limit, which is a safe limit. But the problem with these safe limits is that you try to push them to the right, the higher, the higher, the higher. And if you have these mechanisms, then it's easier to push them to the right than if you don't have these mechanisms. So one of these is changing how the execution layer peer-to-peer networking is working. It's EIP 8077. Changing how we are announcing transactions. Currently, we are announcing just hashes, basically. And then if you are falling behind, you cannot really catch up. With EIP 8077, you have more information. We are sending more metadata, and you can catch up. You can also, it's also useful to do actually partial state. Then there is EIP 8094, which is helping again when we have price volatility. It's helping to use less bandwidth in those cases. And then there is the proposal of blob pool tickets, which is, again, a nice solution to reduce, to avoid congestion on the network. OK. The mempool is, I said, it's an important part because it's not just the scaling. The mempool will be important for a few other things in the following year. There is post-quantum, and we should handle that in mempool. There's the ZK proving, and it has ramifications in the mempool. There is account abstraction, a new type of transactions which are harder to validate in the mempool. We should handle that. There will be fossil, and it has its own ramifications in the mempool. There's stateless or partial state, which very much related to mempool, because again, how you know if a transaction is good or bad. There's swaps for that. And then there are encrypted mempools. So the mempool will be, I think, quite an important part in the upcoming year. Thank you. Questions, I think, off the stage. But thank you.